So welcome to my talk about StringTouch, from string instruments towards new interface morphologies. My name is Rossmy and I'm giving this talk on behalf of my co-authors Sonja Rümelin and Wiethoff. So when we talk about tangible user interfaces and the design of interfaces in the HCI context, most researchers start with familiar mental models and metaphors to create understandable user interfaces. So if you think about understandable user interfaces and familiar mental models, you could think of string instruments, for example. But even if they are really part of a lot of cultures and cross-cultural resource and inspiration, they are mainly unconsidered in the HCI context. So, and if they are considered, they are not like considered as a whole. It's not like the whole instrument morphology which is considered, but it's rather like the string itself or the chord which is taken into account. So for example, user interfaces can attach strings to persons, or we explore how people can actually manipulate the strings and the chords to perform actions. But if the whole instrument is considered, it's rather about how to improve the instrument, how to make it more expressive. But chordophones, string instruments, are a rich resource. We have like a lot of different designs. We have lute type of instruments, the zithers or harps. And the shape, the morphology of the instrument is defining how we interact with them, how we use them, how we play them, how we position them towards our body. So we investigated further and found that some of these, and especially the zither types, have a huge correspondence to modern technology, namely the interaction with touchscreens or touch surfaces or like tabletop devices. So we took that as a starting point and asked ourselves, okay, where do we actually interact with touchscreens, but maybe it's not the best idea or the best context for doing so. And we found a car where more and more touchscreens are implemented. But touchscreens have like a big problem. We lose the passive haptic feedback of the normal user interface. So for example, an old car interior would have like a dedicated knob for volume, a dedicated knob for temperature of the car. And I could learn where it is, I could feel it, but on the touchscreen I have to look, I have to see and have to search the element before I could use it. So obviously when I'm in my car and I'm driving, I should probably watch on the road rather than on the user interface. So we tried to adapt the string context to the shape of the dashboard, and we created a flexible dashboard surface, including and incorporating like string-like shapes along the whole dimension. And via interacting with these strings, you could actually control the media system. So after that, we were interested in, okay, probably there's more to it. There's more stuff you could do with strings. We should probably learn more from string instruments. So we did a research about interactions typically performed on string instruments, and we collected interaction vocabulary. We somehow clustered it and found different interaction types. So for example, gestures corresponding to the excitation, like the stimulation of the string, as well as gestures which are defining the pitch. And there's also an overlap, like actions defining pitch as well as excite the strings. So with this knowledge, we were now interested to explore these gestures to a certain extent in a generic peripheral device. So we created a new USB generic peripheral device where we actually had like a similar approach. We had these kind of ridges along the shape, and we were interested in, okay, what can I do with it? What are the possibilities of the morphology? So I want to show you a quick video demonstration where we actually show you what it can do. as we demonstrated, there are different types of interactions we implemented. So one idea we took from string instruments is that most of the interactions are not really based on an absolute position. So there's not like one specific location on a string instrument, but rather it's more about like the context. So for example, playing a chord and moving the chord, it stays like the same chord shape. Probably you change the pitch, but it's still like the same configuration of your fingers. So we wanted to take this, so we took the concept of pi menus. So you touch a string and then around your finger position you have like UI elements, like generic UI elements popping up, which you can then later interact with. So you, for example, you could push and pull. This is like a gesture taken from the guzheng, the Chinese zither instrument, to, for example, select or deselect or increase or decrease values. And we also explored with like strumming gestures, like strumming along the ridges, the strings, or like sliding along them. To actually track these different kind of interactions, we had to differentiate touch from deformation. So to detect the touch, we captured the capacitive touch via capacitive touch areas in our PCBs. And to track the deformation, we included magnets in the silicon bridge. And if you push into the material, you change the distance from the magnet towards the Hall effect sensor, and you increase the voltage, which you can measure. And the same goes for pulling. So if you pull, you increase the distance between magnet and sensor, and you have like a lower value you measure. So we designed our PCBs in a way that we can easily like make a larger or smaller interface. So it was like modular design, and we could daisy chain multiple of these, and then in the silicon layer we had all these magnets for each Hall effect sensor and a TNC board to actually handle all the data and generating USB messages, which we then can like process on the computer. We were also interested in evaluating the haptic properties of the device. So could the design, the affordance of the silicon ridges actually influence what kind of movements and interactions we could perform with it? And also, could we differentiate different shapes and textures by just like feeling them? So we did a user study where we had blind tests with different shapes and textures, and we tested different widths and heights and strength of the material, and we saw that there is an influence of the design on the interactions which are possible. So for example, a really low design is hard to pull because it's hard to grab, whereas like a really thick design is hard to bend, and so on and so on. So the design is influencing the interactions we can perform, and that's really interesting because we then can, in theory, design our interfaces so that they support the interactions we are intending the user to do. So currently we are also exploring different things. We are exploring like flexible PCB designs with breakable PCBs directly casted into the silicone to enable like free form, free shape interfaces. Another thing which we are interested in is like going back to specific application scenarios. And one would be, for example, making use of the capability of users to differentiate the strings and perform interaction with the strings without direct visible contact. So we could, for example, include them in the back of devices to enable discrete interactions. Or we could use, for example, cylindric shapes and wrap around our silicon surface to enable multiple users from different sides to interact with the interface. So as a conclusion, string instruments are a rich resource of inspiration. So we found different types of interaction, different types of morphologies which we could use or reuse. We also found that the technology we developed, like the capacitive touch in combination with the magnet and Hall effects sensors, could provide a way to avoid the Midas touch problem, because we can differentiate touch from deformation. So we could have a hover state and an interaction state, which is a big problem on touch surfaces. So further, we saw that people can actually feel differences in the different designs, and this could be used to reduce visual attention, which is needed to perform to operate the interface. So thank you very much for your attention, and if you want to get in touch, feel free to contact me Please enjoy the rest of the TI conference. Have a nice time.